exciting. Man.
Yeah.
Let's see, I want I'm going to need to request permission.
Just a little more time ran over in the planetarium show. That was an excellent planetarium show.
It was great.
I
Amazing.
recommend you time to find out. Get on the schedule and seeing it. We got up to ATP. And then a scene triphosphate. Okay.
All right.
Are we ready, Tom?
Not yet.
No?
Okay, let's give it a try from there.
Okay. Can I take this out? That's where the lights go out.
I unmuted the Zoom.
What's that?
I unmuted the Zoom.
Okay, good, good,
Is it really recording?
good. Yeah.
Okay. Welcome everybody to the, what is this, April monthly meeting of the Santa Barbara Astronomical Unit. We have a guest speaker tonight from the Las Cumbres Observatory, Joseph Farah, who's going to speak on everybody's favorite topic, black holes. But before we get to that, we have a little slight amount of business and some commercials to go through. We do not sell our time. So, and the planetarium show was given by Chuck was on the creation of the Earth. Very good stuff. Great graphics. And last Monday, we were treated to or Tuesday it was, no, April 1st. I never trust meetings on the 1st of April, but we made an exception here. And we were down at the County Board of Supervisors building, and they had passed a resolution. It's not a law, but it's a resolution. And it says that they want to encourage people to adopt practices that encourage or lead to dark skies, to try and preserve and recover our dark sky. So Luke Swetlin, who was ill, was planning to be there, but we had 3 people from the club here, and Roy Lee on the side, and yeah, Joan Hartman, but I'm trying to remember that. I confuse it with Wachowski, Mike Waskowski or something. So, yeah. So anyway, it was a good event, and we were happy to support that, and we got a copy of, someone got a copy of that. I don't know where it is, but this is the resolution. And as you know, dark sky, the idea is that when you go to put a porch light out or something, the light should shine only down, and it should not shine down on real bright surfaces like white concrete. Lower wattage things, so that, as Chuck mentioned at the beginning of the planetarium show, so you could walk outside and look up from places like Santa Barbara and you can see the starry sky at night. The internet has got this thing on it where a statement where people panicked when lights went out in Los Angeles and they claimed this big cloud was hanging over the city. And it turned out it was the Milky Way, but they'd never seen it before from the big distant cities. But we're going to go through a few of our club members here. We're going to start with our merchant manager, Pat Porgy,
Yeah.
Pat Partland. Pat Forty's my wife.
Thank you, Jerry. Big Partland, it's close. Welcome all tonight. Looks like we've got a good crowd. We'll try to make this really short so we can go into the talk. I have merchandise, some of it back in the corner there, and I also have it online, as you can see. Not to sell it online, but you can contact me at merchmanagermtr@sbau.org. And I just brought one of the bags with me. It's really cool. It's got a zipper top, has place for cups or bottles to be put into it. Nice bag. Name tags for Astronomy Club members. If your name is not spelled correctly, let me know. I'm the one who puts it together. So if you're a club member, go ahead and come in at the beginning, when you come into the meeting, to grab your name tag and let us know that you belong to the club. Thank you, Jerry.
Thank you, Pat. She's also our financial treasurer, but we're not going to go into that today. Our outreach or not our outreach yet, Chuck, hold it. Our events planner. Do you have anything you want to say today?
Yes.
Diane, welcome back.
Yes.
I'm sorry.
Yes, we have our first event of the year for the SBAU club members and their families, and it's going to be held at the museum on June 6th, which is a Friday, and it will be starting at 5 o'clock sharp, well, promptly at 5. We want to get people there at 5 and start to eat, like 5:15, something like that. And you're encouraged to bring your specialty dish, which we are all very fond of, or if you don't have one, now's the time to get out your recipe book and whip up something. Try it on your friends and family first, and then bring it to the event. So mark it on your calendars, and we'll see you then. Thank you, Jerry.
Thank you, Diane. Tessa, do you have anything you want to say? Tessa's our secretary, takes notes and minutes.
Again, for SBAU members, we still have some directories left. So you can call your buddies and say, you have one of those little gym cracks that would hold together the part of my Dobsonian that's not going right, or other good things like that. So a few more just for members. Thank you.
Thank you, Tessa. Now, Chuck.
Only $1.
Now, Chuck is going to run down our outreach for the month of April. Upcoming attractions. Great talk in the planetarium.
Yeah, sorry, I ran over time there. Too bloody.
All good.
Too many Pleiades stories. Okay, so April's kind of a quiet month, and we've moved some events from our normal times. Normally, our star party here is on the second Saturday of the month, but we're holding it tomorrow on the first Saturday. Starts officially at 8 o'clock and goes till 10. And we'll have scopes set up on the little roadway from the parking lot into the observatory over there. Hopefully we'll have a nice night. All the weather projections look good. Normally that's on the second Saturday of the month. And then we have a couple of schools. Vieja Valley's having their science night. They call it a night, but it ends at 7:30, so the sun will just be going down. So that'll be a case of if you have a solar scope and we manage to get a good eastern horizon, you can show that, or you can just come and talk about astronomy. And then we have a group camping at Kachuma Lake. Some of the details are still hovering around in space, but it looks like it's going to be at Dakota Plains, and for about 20 people, setting up at 7:15. If you get charged an admission fee to come in with your car, keep your receipt and you'll be reimbursed for that, either by them or by us. And usually what happens is we're coming in after they close the kiosk, so they don't even know we're there. So that works out pretty well. Let's see, we have some other schools, but they're just daytime. Then we've also moved, normally we have the third Friday of the month at Westmont, the third Friday star party's there, but they've moved it to the fourth Friday. And Montecito Union School was on Thursday before that. Oh, I'm just going to that during the day, so I guess that's not even on there. And then at the same night that we're doing Westmont, we also have Los Flores Ranch Park, which is up by Santa Maria. Fairly dark skies for being close to Santa Maria. So if you don't want to drive very far, go to Westmont. If you don't mind driving, please come to Los Flores Ranch Park. Although we'll have people there from the Lompoc Astronomy Club and from the Central Coast Astronomy Club in San Luis Obispo. And then a big event that we'd like to get some telescopes out for is on Sunday the 27th. It's for the whole San Ynez Valley. Telescopes for a star party setting up at Los Olivos Elementary School. So that might be a biggie. They're still kind of hashing out the details on that too, but as far as we're concerned, we're showing up there at 7. Thank you.
Thank you, Chuck.
Just want to point out about Astronomy on Tap also on Thursday the 10th. And Joseph, are you going to be there?
Yes, I go to all.
Oh, very good. So it's at the, what's it, M Special on State Street. It's always fun. LCO puts on a nice show and makes fun of the news.
Well, periodically we get called, we get invited up to do an outreach at one of the vineyards up in the San Ynez Valley. And those are really cool because they usually give us a bottle of wine each. So,
Also want to point out, Jerry, equipment. We do have some equipment available. So if you're looking for a telescope or some accessories, check in with us. And one of our members has a whole set that he's trying to sell. He's lowered the price to $1,400 from $1,700. So
these are listed online, are they not?
I will try to keep them on our page. It says equipment for sale. So
Okay.
all right.
Tom is our webmaster, and he's the person that takes donations of telescopes and sells them if he can.
We'll pass
So
them
it's
on.
been pretty good. Now we're going to have our vice president come up here. Well, okay. And he's going to introduce our speaker for this.
We don't?
We need a longer way.
Person right there? I have it right here.
Well, we're gonna get one.
Oh my God, what happened?
The triumphant return of Joseph Farah with one R. I misspelled it for a while, but he came and regaled us, dazzled us a couple of years ago. Many of you may have been here when we overflowed this hall, and we're pretty damn near as much as we can get. We didn't turn anybody away, did we? Hope not. There's nobody out there. I got a few things I got to run through. Number one, I need to have you at some point, maybe at the end of your talk, Joseph, tell us how you did at yesterday's grad slam.
It did not go well.
Oh,
I'm assuming that's sort of like the old GE College Bowl. Is that
Yeah.
questions and answers? And
No, it's a thesis talk, a 3-minute thesis talk. It went smoothly, but there were better presentations, and it was a lot of fun, but I didn't win anything.
Okay. Well, I was going to drop in. That was about 3 o'clock in the afternoon. I got a couple things I want to talk about. His talk is the black hole explorer and the edge of the universe, because he was involved in the first talk with getting the first photo of our big centralized black hole, the supermassive Sag-A star. And it looks a lot like the other one they got in some other galaxy. There's a big orange blob around it or something. I got to run down the people who are going to be speaking to us in the future. And I want to invite you all and thank you for coming. And if you'd like to join, I always ask for a little show of hands. I'd like to know how many people in this room right now are members in good standing with a card of the museum. Raise your hand if you're a museum member. Okay. Now raise your hand if you're a member of the SBAU.
okay.
Notice it's not really a majority. Now raise your hand if you're a first timer, first time you've ever been here. Okay. You're the ones we want to get. And we will. We're going to remember you. I want to pay tribute to Diane. She's a horsewoman. Tessa has been in the solstice parade. So you're going to meet some great people if you join this club, gang. $20, which is about the cost of a meal at a restaurant with a drink in Santa Barbara these days. And You know, can I give you a secret? It's free if you go to a lot of outreach. Because I don't pay. I'm starting to, I'm going to volunteer. I host a podcast, a blog on the Monday mornings, and I'd like you all to try it out sometime. It's SBAU Astro Hour. We've done 4 years worth, and we've just started our 5th year. It's 52 weeks in a year. Do the math. We're doing number 214 on Monday morning at 11 a.m. They're all saved on the YouTube and I think in our SBAU.org archives. Old friend of mine showed up. I wasn't expecting him. We're going to get him. Former Supervisor Greg Hart, now in the Assembly. You want to raise your hand, sir? Is Sean Kelly here, who's a member?
He's not.
What?
He's not.
He's not.
Oh, he's not here? He runs the astronomy department.
Yeah, they're out by the top of Eking near Seattle right now with the star party looking at the stars.
Well, that's a cheap excuse. Fly it once, but never again. He's got to be here. Who am I forgetting? Oh, part of the equipment you saw for sale there was owned by a friend of mine who is in the club that rarely comes. I wonder if he's here. David Grossman used to run the PR for the symphony orchestra for many years. I'd get to interview him on the radio. Now he's in the club and he's written not 1 but 2 cover stories for Astronomy magazine. And it's about sounds in space, something called sonic or sonos or something like that. I don't know how, the man's into drugs or mushrooms or something. But he's a good guy. So let me tell you who's coming in the future, and then I'll bring on Mr. Farah here. Next month, May 2nd, Dr. Katie Wimberly, very friendly looking lady. Cal State San Bernardino, going to talk about dwarf galaxies. Oh, is he matching me on the screen? Man. June 6th, the following month, is our June picnic. Now there's a reason to join. Get to the club, pay your $20, and you get a free meal. You just have to bring a covered dish. We eat over there behind the, right next to us is where we eat, next to the river, the creek. On July the 10th, which is a Thursday, for some reason we couldn't even do the first Friday of July is the 4th, so we can't do it. We don't have enough pyrotechnics. And when they tried to move it to the 2nd, which would have been the 11th, and that wasn't possible, so it's now a day before that. Thursday, July 10th, you're definitely going to be here. Dr. Martin Cacan, C-A-C-A-N, who happens to be our president's godson, was the pilot of the NASA helicopter on Mars, which was called Ingenuity. That went up with Perseverance. It's now sitting there not being used, and if you send any kind of a control joystick electronic signal, it takes, 30 minutes to get there? I don't know how. He's going to answer all those questions on the 10th of July. And then to wrap it up, the last month of the summer, August 1st, Dr. Stephen Kane of UC Riverside going to take us all out to our very hot sister planet Venus. His talk is actually habitability, or the ability to habitate planets. So now, without further ado, is Isla here too? Isla? There you are. She's our connection. We love her. And I'm getting along with Owen, the man in the PR section, and a PhD student on his way 1 more year in astrophysics at the university studying supernovae with Dr. Andy Howell of LCO. He's part of Los Cumbres Observatories and the Global Supernova Project. He just received his BS in physics, right, from the University of Massachusetts, Boston, 21. He worked on the Event Horizon Telescope project as a Smithsonian Fellow and at the Harvard Smithsonian Center for Astrophysics under the supervision of Michael Johnston. He helped produce the first image of the black hole, M87, that led to, is that what it's called? Is it a Messier? Messier saw it. Well, anyway, the picture of the Saggitarius A star in the center of our Milky Way, and this is going to be a continuation of that theme. For his work, our guest speaker was named a Barry M. Goldwater Scholar co-recipient of Breakthrough Prize in Fundamental Physics. In a couple weeks as I wrote all this down and I'm reading my small print. Winner of the 2021 Leroy Apker, is that the name? It's an award. I'll let him tell you more. Joseph Farah, ladies and gentlemen.
Can you guys hear me okay when I talk like this? Yes. Sweet. I'm going to switch over to the. Can we, Tom, can I switch over to the?
Yeah, find that other
Thank you.
source. Come on, find him. There you are.
Ah, sweet. We're good to go. Thank you, Ronnie and the SBAU for having me out here. I also want to say thank you to my advisor, Andy Howell at LCO. He's given me a ton of freedom to work on this stuff as my side hustle. And I just want to say thank you, my advisor on this project, Alex Lipstoska. But I also have a special thank you to you guys. So to give me a chance to talk about this stuff tonight, I'm really genuinely excited about this work, and it's such a privilege to be able to talk to you all about the Black Hole Explorer and where this space mission stands and what we expect to see. And you know, it's been a dream of mine since I was a child to work on a space mission, and so it's kind of hard for me to believe that I get to stand up here and talk about this really cool project. So thank you guys so much for being here. Let's get into it. Okay, so if you've read anything about cosmology, about our picture of the universe, you probably picture something like this: a universe that's expanding like a balloon. It's got no boundary, and that no boundary comes from the fact that if you lived on the surface of a balloon like this, you wouldn't really perceive any boundary because you just keep walking around and around, and you wouldn't fall off an edge, unlike the Earth. But actually, this picture overlooks something, which is that the universe actually does have an edge, not in the flat Earth way. What do I mean by an edge? Well, we have this property of the universe that massive objects attract each other. This is called gravity. And Einstein showed us that with general relativity, that a massive object bends space-time around it, and then other objects kind of fall into this gravitational well, this dip, and appear to interact. And the effect happens on small scales, like as small as tiny particles interacting. I made my students do a calculating how weak the gravitational force is relative to the electromagnetic force, and it works on that scale too. But also, and I would argue more importantly, on large scales, on the scales of the universe, the largest scales of the universe. And gravity actually is the largest, it's the most powerful force in the universe, because on large scales it can't be stopped by a negative mass. So even though the forces like the electromagnetic force or the strong nuclear force are many, many, many times more powerful than gravity, because you can have a positive charge cancel out a negative charge, they can go to zero, but nothing really ever takes away the force of gravity. It just keeps going on and on and on. Gravity has this unique property, or not unique, but it's got this nice property that it only ever attracts. So the more mass you get, the stronger the gravity becomes, and that attracts more mass, which makes the gravity stronger. And there isn't really a limit to how strong the gravity can get. There are practical limits, like how much matter there is in the universe or around you, but there isn't a theoretical limit that says, oh, here's a number, here's a cap. Eventually, if you keep shoving more and more mass together, the gravity's going to get stronger and stronger. And eventually, you'll get an object that you've probably heard of, a black hole. And a black hole is this object that has so much mass that it's compacted in such a small space that not even light can escape the pull of its gravity. And that sounds like a really mind-blowing concept, but to be honest, that's not even that weird. Ever since we understood gravity, which has been for a pretty long time now, a couple hundred years, we've understood that the more mass you have, the more gravity you'll have. The more gravity you have, the higher something called your escape velocity will be. So, if you want to escape the gravitational pull of a massive object, you have to travel faster than its escape velocity. For the Earth, That's about 7 miles per second. So if you want to send a spaceship in space, you got to achieve a 7 mile per second velocity. So it's not that it's not that crazy to think, okay, you keep putting mass in, you'll eventually get past the speed of light, which is very finite. And actually, in the 1700s, the idea of a black hole was hypothesized. It was called a dark star, a star that tried to emit light, but its gravity was so strong that the light would just fall back on its surface. So black holes are interesting, but they're not even that weird until you get to sort of the advent of general relativity. And our subsequent understanding that gravity is an effect caused by the curvature of space-time itself. And it was then we realized that something strange happens inside a black hole. So as the mass grows and grows, its gravity gets stronger and stronger, and the curvature of the universe becomes more and more extreme. Eventually, you get an event horizon, where because you can't travel faster than the speed of light, no signal can escape beyond this region. But right at the center of the black hole, the equations that govern the curvature diverge to infinity, producing this weird thing called a singularity. And in a strange moment, the universe kind of bends and bends and bends and bends, and then it kind of just rips at one point. And that's at the singularity at the heart of the black hole. You can almost imagine a little pop as this like point that was once in the universe gets removed. What do we know about the singularity? Well, we know it's an inevitability. It's not so much a point in space as it is a point in the future shared by all travelers who enter the black hole. Anyone who falls in, the singularity inevitably lies in their future. But it's really weird. It's this spot in the universe that you can reach in finite time, but it doesn't exist in the way other places in the universe do. In GR, we'd say it's a point that has been removed from the manifold of space-time. I find that so weird. Like, it's so weird. In a very real sense, it represents an edge to the universe. Not an edge you could go to and like wave to someone on the other side, but a boundary where our understanding breaks and space, time, and predictability kind of cease to be meaningful concepts. Ever since I've learned that our universe has an edge, I've been really desperate to answer 3 questions. What does it look like? And can we take a picture? And Instagram. And what lies beyond? So we can try to answer these questions with 2 theories that we have that describe the whole universe. Einstein's general relativity, which we use for really, really big objects, and quantum mechanics, which we use for really small ones. The difference is much more nuanced than that. But that kind of covers it. Like, if you were talking about the orbit of planets in the solar system, you'd use GR, you wouldn't ask QFT. And if you were talking about an electron passing through 2 slits, you'd use quantum mechanics. GR would be functionally useless. And they work really well, these 2 theories, and they, together, describing all the big, the small, the slow, and the fast, they kind of cover our whole universe. And they work really well. And that's not a good thing. And I'll explain why. So we've tested them again and again and again across so many scales and regimes. I've just selected a couple of the many, many experiments that we've done to prove that these theories work extremely well, to highlight just how correct these theories are. So, the classical GR test was the Eddington experiment. Einstein predicted that light should curve around massive objects in a very specific way, because even though light has no mass, and so maybe it shouldn't be affected by gravity, if you imagine that gravity is the curvature of the universe, well, light's going to follow that curvature regardless of if it has any mass or not. So, Einstein predicted that if you look at some stars in the sky, and then you look at them again in a solar eclipse, where the sun is there, but it's not blinding you with its light, the stars will have moved. Their positions will look a little different because their light is being bent, like the light bends through a pool of water, by the sun's gravity. And he was exactly right. Eddington went out and did this experiment. He schlepped out to take some data during a solar eclipse, and he found that Einstein was exactly right. It's like 1%. And then we got even better experiments like Gravity Probe B, where we had these incredibly sensitive gyroscopes around Earth, and we pointed a telescope inside the satellite at a star, and we had predictions for how much Earth's gravity, based on general relativity, would wiggle the telescope as it looked at the star, and it exactly matched predictions. So Einstein was right again in one of the most sensitive tests of general relativity ever. But quantum field theory and quantum mechanics is no slouch either. In the early 1900s, people were coming up with experiment after experiment to show these incredibly bizarre properties of light and particles that everything in our universe kind of behaves as both a wave and a particle. That evolved. I mean, we have so many experiments testing this, but very, very recently we had the muon G-2 experiment. And they showed an incredible precision that the muon, which is a heavier electron, wobbles in a magnetic field to test the predictions of the standard model, which we have someone in the audience, Liam Brennan at UCSB, who works on this kind of stuff. And even the tiniest discrepancy from the standard model could be detected many, many orders of magnitude of precision, higher than any experiment before. And had there been a deviation, it would have pointed to new physics. But boringly, the standard model was right again. And so even on the most, the finest scales, the highest precision you can imagine, these two theories are right, over and over and over again. For all intents and purposes, that is a correct, that's their truth, is how we can think of it. That's really important because we've used these theories a lot. And very bad things happen if they fail. So like your cell phone is entirely like based on the principles of quantum mechanics, how we're able to squeeze tiny high-resolution screens and processors into a device, the size of a potato chip. That's all quantum mechanics, basically. And then how that device connects to satellites orbiting an Earth at a non-trivial fraction of the speed of light, causing them to experience time dilation and slow down, all general and special relativity. And more so than just useful things, which personally I have no interest in. These theories also give us all the information we have about how the universe was born, like all the way up to 10 to the minus 135 seconds after the Big Bang, which is a very, very short amount of time. All the way to how it evolved to its present day, going through its stages of radiation, matter domination, now dark energy domination as it accelerates continuously, until its eventual death, as everything eventually gets sucked into black holes, and then those black holes evaporate via Hawking radiation, leaving behind a sea of colorless noise. Sorry. That took a long way away, so continue to enjoy your lives. But all this stuff that I just said, which we're pretty sure about, is based on these two theories being right. So I hope I've convinced you that it would be really bad if either of these were wrong. Okay, so why do we care about whether or not why am I bringing this up? Well, black holes are kind of weird, right? I said that we use GR for really big stuff, and we use quantum mechanics for really small stuff. That was an oversimplification, but not by that much. To give you some perspective on how big black holes are, and you'll see why I'm bringing this up in a second, if the average human being is about 10 to the 1 kilograms. If you're in America, probably more like 10 to the 2. For comparison, the Earth is about 22 orders of magnitude heavier than that. So take 10 followed by 24 zeros, or 23 zeros, and that's how big the Earth is in terms of mass. And if you took it and squished it into a black hole, you would get a black hole about the size of a marble. So that should give you the idea of the density that you need to achieve a black hole. You can do the same thing with the sun, and we found lots of stellar mass black holes thanks to LIGO and stuff. And if you did the same thing, you compressed it into a black hole, which we now know we can by supernovae, you would get a black hole about 2 miles across, which is about the size of Manhattan. So black holes are these things that are both really, really, really heavy and squished into a tiny, 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 tiny space. So you can kind of fairly say you can ask both of these theories what happens. And a black hole is actually the only place in the universe where you can fairly ask what happens. You fairly ask both of these theories for an answer to the question, what's going on here? So we do that. We ask general relativity, hey, once you get past this event horizon, what's going all the way down to the singularity, that edge, what's going on? And you can ask quantum mechanics the same thing. And they disagree. They give completely different answers. And honestly, to some extent, the answers are kind of nonsense. And that is really problematic. Because now that we know black holes exist, we know that there's a place in the universe where we're wrong about these two extremely important theories. And so a great mystery emerges. Which theory is right? Are they both wrong? Which would be a catastrophe, and it was also the most likely correct answer. Honestly, we're lost. Like, this is the greatest open mystery in physics, the disagreement of general relativity and quantum mechanics in the most extreme environments in the universe. We've had attempts at trying to resolve this You may have heard of some of them. One of them is called string theory. It's a kind of a nice pop-sci topic, but it's an attempt to come up with a theory of everything that doesn't start from assumptions that violate the other theory. So, quantum mechanics kind of starts by assuming that the universe doesn't really curve, and that's like already a problem. And general relativity is like, kind of assumes that everything looks the same on all scales, and the universe is just one smooth mesh. And both of these assumptions violate the other theory. The theories like superstring theory and loop quantum gravity try to say, okay, what if we started with all the assumptions for both theories and built a common theory that works? And they've made really good progress, but we're nowhere near a testable theory. Part of the problem is how do you test this, right? GR and quantum mechanics work super well on every scale we could possibly probe, and where they fail is a scale that we don't really have access to, black holes. So we can't really test either of these guys, but there's another route. We can't create a black hole on Earth, but some of us went in a different direction. Can we try to take a picture of one and use that to test these theories in an experiment many times more intense than anything we could hope to create in a lab? So that was what the goal of making these kinds of images is. Could we try and take a picture of this edge of the universe? What do we expect it to look like? Can we get a clue about the mystery of whether GR or quantum mechanics is right? And that's what began the race to see a black hole for the first time. So, astronomers for decades have been looking around the universe for what they thought were good spots to find black holes. And one of the easiest targets is the center of the Milky Way Galaxy. In every galaxy we've ever looked at, there's a big, big, big black hole in the center of it. There stood to reason that there'd be one in the center of ours, so we found the brightest spot in the center of our galaxy that had a bunch of stars orbiting it, and we zoomed all the way in, and we, spoiler alert, that's our picture of the black hole in the center of the Milky Way. I've sort of told you already that, black holes are really, really small, and they're also really far away. So, out of curiosity, who here has seen the first image of a black hole, the one that doesn't look like this, M87? It's like also a fuzzy orange donut, but okay, yeah. So that one was way farther away than this one. This one is just 25,000 light years away, but M87 is 55 million light years away. And I just told you that black holes are really small. So a fair question is, how do we create these images? And so I'd like to introduce you to something called interferometry, which is basically magic, and no matter how long I work on it, it will never seem to be less so. I'm working on it for a better part of a decade now. So you guys are pretty, I know a lot of you guys are really familiar with optical telescopes, but you may be less familiar with interferometers. So let's do a quick review. This is a telescope. It has a certain size, d, and it observes at a wavelength, lambda, which is, for optical wavelength, that might be 550 nanometers. For radio wavelengths, it might be like 1.3 millimeters. But the point is its resolution, which is how small of a thing it can see on the sky, scales with these two numbers. If you want to get a better resolution and see something sharper, you can make your telescope bigger, or you can decrease the wavelength that you're observing at. For like the purpose of this, let's just think about making the telescope bigger. Interferometry lets you connect two telescopes together into a network, or an interferometer, and their resolution is now no longer a function of how big each telescope is, but rather the distance between them. And this immediately leads to a life hack, which I'll explain in a second. But there's a little problem. Even though it's really convenient, right? You don't need to build a huge telescope. You can just take two small telescopes, link them together via this witchcraft, and place them on opposite sides of the planet, and you've got an Earth-sized telescope. But there's a slight problem, which is that when you do this, the telescopes no longer can see the image of the black hole, or your target, like a regular photo your camera would take. They instead see properties of the wave that bounces along the line between them. This line between them is called the baseline between the two telescopes. And the quantity that the telescope sees is now no longer this, brightness on the sky, it's this complex quantity telling you how powerful the electromagnetic wave is and its phase. It turns out that quantity is intimately related to something called the Fourier transform. So if you take an image of your source and then Fourier transform it, which is this mathematical transformation that tells you how to make this image out of a bunch of sine waves, That's what an interferometer sees. So you can imagine your baseline has some size and angle. And it turns out that the size of the baseline and the angle it observes at, this quantity V that it measures, is exactly the brightness of that point in the Fourier space. This is not that important to really internalize. I'm just trying to communicate how weird, how much harder it is to make an image out of this, right? Because we now have to invert this thing to get our image out. And that's fine if you have all the information, but we don't. What I just showed you here is we put, spend tens of millions of dollars and put 2 telescopes to get 1 data point. And you need all the data points to try and invert the image. We have tricks. So, if you place many telescopes together in a network, they each have baselines connecting them, and then those baselines probe different parts of the Fourier transform. So, if you start placing telescopes all over the world, which is what we did, you get this dense network of baselines. And you can probe that weird Fourier transform thing and get an image out. And it's a blurry image because you don't have all the data, but you need to make a really sharp one. But it is an image nonetheless, and a real image. You may have heard that it's like a fake photograph, or it's not real, or it's a simulation. It's not. It's a real image. But like the telescope doesn't have glasses on. So you can see the life hack here is we took telescopes and put them as far north as we possibly could. That's our telescope in Greenland. And as far south as we possibly could. That's literally our telescope at the South Pole. And as far east and as far west as we could. We have a telescope, 2 telescopes on Mauna Kea in Hawaii, the sub-millimeter array and the James Clerk Maxwell telescope, and telescopes in Europe, at IREM and NOEMA in Spain, and I forget where NOEMA is. So the fair question is now, what kind of resolution? We've done all these tricks. We've accepted the burden of having to invert this magic Fourier transform thing and get our image back out. The question is, what resolution did this buy us? How good can we see? So, let's first give you some perspective. The human eye, the little thing in your head, has pretty good resolution for an organic, ball. And the way you can think about the resolution of a human eye is if you took a credit card and stood on the opposite end of the football field, you'd be able to see that the person is indeed holding a credit card. You wouldn't be able to see the numbers or anything, but you could see like a vague, capital 1 colored rectangle. And so that's about the human resolution of the human eye. A credit card at 300 feet. I'm at 20 minutes, so I want to do a quick check-in with you guys. Last time I spoke here, I gave Eminem's Rap God a run for his money because I talked too fast. Is this one going better? Can you guys do it? Okay, sweet. All right. Okay, so that's the resolution of the human eye. What about a home telescope? The SBAU folks in here probably recognize this. You can get it from Best Buy, and it's like a nice starter telescope, Bird Jones design. So the image is crap, but this was one of my first telescopes ever, and I still love this thing. It had a little mount you could put your phone on and it would show you. It was a great, wonderful gift. And anyway, if you this is like a $200 telescope you can get literally just walk into Best Buy and get, and it could see a credit card if you were standing at my house in Goleta from where you're sitting right now. And that's pretty impressive. So you go 10 miles away and hold the credit card, and you can see it pretty decently with this telescope. Again, no numbers or anything, but you can see it, you're holding a card. Now what about something proper like the Hubble Space Telescope? Well now, you can see a credit card. If you can see like the Hubble Space Telescope, you can see a credit card in LA from where you're sitting right now. So the question is, what are we talking with the Event Horizon Telescope, right? How much more resolution do we buy? How far away do we place this credit card and still see it with the EHT? Fun fact guys, I grew up most of my life in Boston, Massachusetts. And if you hopped on a plane and flew all the way out to Boston and landed and held up a credit card, the EHT would be able to see it from where you're sitting right now. But unlike all those other telescopes, EHT would be able to read the numbers off the card for you, and steal your identity. Which is the real reason we built it. But that's it. That's the resolution that we gain going to this interferometry approach. You go from being able to see something 100 miles away to being able to see it across the country. And that's how we go from being able to see, large galaxies that are far away with great detail to being able to see a tiny black hole in a dusty elliptical galaxy 55 million light years from Earth. Some more analogies. if you could see like the Event Horizon Telescope, you'd be able to see Neil Armstrong's footprint on the moon from where you're sitting right now. Another equivalent is you could see an atom held at arm's width. Wow, that atom does not show up well. But yeah, like kind of think about that, right? You held out your hand and there's an atom there, you'd be able to see it if you could see like the Event Horizon Telescope. That's the resolution we're getting at. And it's that life hack of interferometry that gave us these two images that you've seen, the first and second images of a black hole. They're fuzzy orange donuts, and even with all that resolution, they're just enough to see this black patch in the middle of both called the shadow of the black hole, where light goes in and it never comes out. But it's enough to confirm that there is indeed a black hole there, and not some other weird horizonless thing. And so the best we can tell with this, GR seems to work. It matches predictions. But we have to admit that this image is a little blurry. We did a lot of outreach after we released the images, and one of the common, very endearing and well-meaning comments we got was people telling us like, "Did you try playing with the focus?" And we did. The images that you're seeing here are actually just 4 by 4 pixels across. So they're just 16 pixels, just enough to see that shadow. And that's why they look so blurry. But don't worry, this 16 pixels cost about $80 million US, which sounds crazy, but then you remember that this image was seen by about 4 billion people, thanks to Google putting it as a Google Doodle, and it's used as people's profile pictures and for memes. Not that memes are worth $80 million, but like in terms of reward to cost ratio for like impact on the world, this is like the highest in science, period. Like the LHC $1 billion project, Hubble Space Telescope $1 billion project. So this is actually pretty cost effective. Okay, so but it is blurry. So all of us were thinking, even though it matches predictions, like this is a general relativistic magneto-hydrodynamic simulation, which basically means it takes the principles of hydrodynamics, which is like fluid flow, and then adds in magnetism, and then adds in general relativity, and you get very accurate simulations of what we expect the world around a black hole to look like, and they look exactly like what we got. So GR seems to work, but it is blurry. So what if the image wasn't that blurry? It could go sharper somehow. What would we expect to see? So we took our GRMHD simulations, and for example, these are provided by Charles Gammy at the University of Illinois Urbana-Champaign, and his wonderful students. And we can make these simulations of all kinds of black holes. And not a lot we can get from that. Like they kind of just all look different, which is not good. We're looking for features that we can latch onto and say, this is something we want to see. But something really cool happens when you take all these simulations and then you average them in time, and you look at the average image. All the moving stuff goes away, and you're just left with this incredibly thin and bizarrely bright ring of light, which is not something you'd expect for an object that supposedly sucks in light and never lets it back out. Instead, you get this perfect circle of light, and this circle of light is visible, looking exactly the same, no matter where you view the black hole from. So that's kind of wonky, right? There's nothing else in the universe where you look at it from every angle and it looks exactly the same. But this little ring of light does do that. And it turns out this ring of light, we gave it a name, and we called it the photon ring. And it's created by a very special and amazing process. So a black hole's gravity is so strong that it bends the light that's traveling around it. So here's a little animation of what that looks like. If you imagine light traveling from around a black hole, some of it's going to get very weakly lensed. So we call this direct emission. And basically, it makes up the majority of the light that goes around the black hole. And it's not that sensitive to the black hole's gravity because it's only getting weakly bent. But if you get just the right trajectories, some photons will orbit half time. We call these at n equals 1 photon because they orbit 1/2 times around the black hole. And because they're on a narrower set of trajectories to achieve this half orbit, they create a thinner, brighter ring. And you can keep doing this. What about photons that execute 2 half orbits or 1 full orbit? Because this is the n equals 2 photon ring, and it's even thinner, and brighter. And when you add all of these photons that are orbiting together, you get the image that we saw, where you have a sort of big field of emission, and then on top of it, no matter what angle you're looking at the black hole from, a crystal clear ring of light, the photon ring. So these these photons are coming from, this ring of light is coming from photons that are being forced to orbit the black hole due to its gravity. So everyone was really excited about this. In 2020, there was a huge burst of excitement for trying to understand this photon ring better. I, along with my collaborators, published a theory paper showing that you can make precise measurements of a black hole's spin from the shape of this photon ring. So it looks very circular, but actually it has a slight deformation, and we can use that to measure spin. And then at the same time, a team at the University of Arizona, led by Sam Gralla and Alex Obsaska, both of whom I now work with, they showed that you could actually measure shapes like the photon ring using interferometers in a very beautiful and elegant way. And then they published another paper showing that you could actually measure this shape precisely enough to test general relativity and measure things like the black hole spin. Then my current supervisor, my supervisor at the time, Michael Johnson, Alex, and a bunch of others who were working on photon ring science published a paper that would kind of set everything off. It was called Universal Interferometric Signatures of a Black Hole's Photon Ring. And we proved that you can measure the photon ring of a black hole in the center of the Milky Way if you took the Event Horizon Telescope and extended it to space. So that's how the Black Hole Explorer was born. We realized that with sufficient resolution, you could measure this shape. When we did this calculation, we did run into a problem, which is that the ring is very thin. So we do these simulations, and with the Event Horizon Telescope, we could get this image out. But how far into space would we need to go? How much bigger than the Earth would we need to go to get this image out? And obviously this is a problem because the Event Horizon Telescope was already the size of the Earth. So anything else is going to be a challenge. But this was the birth of the BHEX project. The Black Hole Explorer, in the next 10 years, will launch. We're going to design, develop, and launch this orbiting radio telescope. And we'll have an orbital radius 3 times larger than the Earth itself, which will give us enough resolution to see those amazing photon rings. And it will interface with the Event Horizon Telescope and take the first image of a black hole's photon ring, getting us closer than ever to solving this mystery in physics. So it will help us bring our images from this to something more like this, where you can very clearly see the photon ring. So once we have this telescope in space, we'll be able to make images like these. And we're building this thing right now, like at this moment. We just got finished up a conference in Japan a couple months ago. These are some of the leaders of the collaboration. I'm up there in the Zoom meeting. I was unable to make it to Japan, but it's a huge team of people. It's a global telescope, now a space telescope, so it takes a global collaboration. So we have over 150 members, dozens of countries and institutions, all collectively working together to build this space telescope. And we've got prototypes of the dish, the communication system, all this stuff going. And we're right now in the process of submitting a $270 million NASA Small Explorer mission proposal, which will allow us to build the telescope and put it in space and make this really cool image. And this has been an amazing experience because I've always wanted to work on a NASA mission, but it's definitely very intense. NASA is they're very engineering minded. Scientists are very idealistic and like to kind of just get all loopy about stuff. But engineers are like, what can you do if this breaks? Or that. And so NASA has these things called technological readiness levels, which we have to meet progressively as we go through this proposal process and building the spacecraft in order to convince them that we're ready to fly. And I wanted to share this because there's a really funny analogy for the TRL stages. So if you're imagining finding a unicorn, TRL 1 is like, just kind of asking, what if unicorns were real? TRL 2 is, we haven't seen a unicorn, but we've drawn one. That's like our simulations. We know what we expect them to look like. TRL 3, we have made the unicorn in CAD. and we think this is a final design. TRL4 is all of the prototype, so we've taken a horse and then placed a horn on it, and it looks kind of like what we said. TRL5, we put the horse outside, and it seems like it's still surviving. TRL6 is like, okay, you've made it, you may now call it a unicorn. And then TRL7 through 9 is, can we launch it into space at a high velocity? And then TRL9 is like, full success. So it's very different from kind of what I'm used to in the science world, where you're used to a proof of concept with some simulations and you're done. But it's really amazing and intense experience. So what will we be able to do with BHEX? So the goals of BHEX, we have 3 primary goals. 1, we want to answer the question, how do black holes look? We know how they look with massive myopia, but we'd like to know how they look if we play with the focus a bit, get the subject and the background nicely separated. And that's kind of my area of research, is the photon stuff, using it to measure spin, and I'll get more into that. But the next question we can answer with BHEX is, how do black holes shine? So one thing I haven't talked about at all, because it's not my primary research interest, is black holes launch these massive jets. So one of the really fun things about M87 and why we thought there was a supermassive black hole in that galaxy was, if you look at images of it, you can see a huge jet coming out of it. And this was spotted back in the early 1900s. And it turns out we've taken images all the way down, and the black hole is causing that jet. And we don't really exactly know how we go from a black hole, which is supposed to suck everything up, to basically a giant pump hundreds of thousands of light years across. And we would like to know how that works more, because it's important for questions about the evolution of the universe. As is our 3rd mission goal, which is to answer the question, how do black holes grow? So with the Event Horizon Telescope, we, with all that resolution, all that money, all that work, is 350 people from around the world working for over 2 decades to build the Event Horizon Telescope. We got 2 images, because those are the 2 largest black holes on the sky. Even at our resolution, we can't see anything else. Everything else just looks like a fuzzy blob. But with BHEX, we can make dozens of those donut images. We have a figure in our proposal called the donut tray that shows all these simulated donuts we can make for many black hole sources. And if you can see the donut, you can make inferences about the size of the black hole, its spin, and all this stuff. And that's really powerful, because if you can measure a black hole's spin and its mass, you can learn stuff not just about how black holes grow, but how the universe grows. So for example, if we look across the universe and we find that supermassive black holes have very high spin, it tells us that they get their spin by sucking in stuff, and the angular momentum of that matter that they're sucking in contributes to the black hole's angular momentum, and they keep spinning faster and faster and faster until they hit their limit, basically. But if you ever play pool, you know that when you put top spin in a ball and it hits the edge of the table, some of the spin gets taken away, and it's spinning a little slower when it bounces off. And it turns out the same thing happens with black holes. So when black holes collide, unless they are exactly oriented the right way, which is very unlikely, they lose angular momentum. So if we survey the universe and we find, all the black holes we see have low spin, they're spinning very slowly, then we know, okay, black holes are forming and growing to the size by merging with other big black holes. And we've seen pictures of this where galaxies are merging and there's supermassive black holes coming to merge together. So there's so much science that we can do with BHEX. Here's some stuff about the mission itself. This is a preliminary render of the spacecraft by Lockheed Martin, which will be helping us build the spacecraft along with a lot of other amazing institutions. But the idea is we're probably going to have an antenna that's about 3 meters in size, which doesn't sound that big, but we have pretty good noise budgets because we're in outer space and we don't have to worry about the atmosphere or people leaving their porch lights on. So we're good. And we're going to observe simultaneously at 2 frequencies to maximize our data output. And we will have an orbital altitude of 20,000 kilometers. So our longest baseline will be about 20,000 kilometers plus the diameter of the Earth, so about 26,000 kilometers. And that is much, much larger than the EHG. That's the radius there, is 12,000 kilometers is the diameter of the Earth. Where's miles? I'm sorry, Isaac. I'm forgetting how big the Earth is. I'm experiencing so many numbers for this proposal. But at the end of the day, we're going to achieve around a 6 micro arc second resolution via this hybrid space-ground interferometer. To give you some perspective, the EHT resolution, which got us those wonderful black hole images, was about 20 microarc seconds. So we're going from 20 to 6 just by putting the spacecraft into orbit. We're planning to launch in 2031, and then when we do, our orbital configuration will look something like this. So we're going to have all these red points correspond to components of the Event Horizon Telescope that we'll be interfacing with, and these yellow stars correspond to our beta downlink, which I'll talk about in a second. But BHEX will follow these orbits and connect with different parts of the telescope at a time, over time helping us flesh out that Fourier transform and get more data to convert it to a sharper image. And we hope to be able to go from images like this to images like this. And if you compare it to a raw simulation, you can make out, just barely, the photon ring itself from the background. And that is extremely exciting, because that's how we're going to measure spin and do all this amazing science. So I mentioned the data downlink. There's a lot of challenges involved with this project, but one of the most fun ones is our data problem. So an interferometer produces a lot of data. It's actually, the Event Horizon Telescope was actually the largest physics experiment by amount of data per night of observation in the history of physics. So to give you some perspective, your average phone or laptop might have a couple hundred gigabytes of data. A terabyte is 1,000 gigabytes, so you can imagine taking 1,000 phones, and that's a terabyte. And then a petabyte is 1,000 terabytes, it's like 1,000,000 phones. The ESG produces about a petabyte of data every night. And you can't store that on the spacecraft. It's actually so much data that we can't even work with it on the ground. Like, you can't upload the data from our sites to like a central server or something, because it would take 30+ years over a Wi-Fi connection. We have to physically bring these hard drives and put them on planes and fly them to our supercomputers. And that was part of why the first image took so long. There's only 2 flights a year that fly out of Antarctica, bringing our data with it. And so we had to wait for that data to get to us. But the founder of the collaboration, Shepard Billman, he likes to say that when he's running down the hall with all the data, he's the fastest mode of information transfer ever conceived. And he's not wrong. He raised 4.5 petabytes of data, 60 feet in 2 to 5 minutes. I don't know how long the hall is. But, so how do we solve this problem with our spacecraft, right? We can't actually keep this much data on there. We'll get corrupted by cosmic rays, and also we want our spacecraft to be as light as possible. So having hundreds of pounds of hard drives is just like the worst way to go. Also, you don't want too much storage. Like I said, it can corrupt easily, and we want this thing to be out there for a long time. So we came up with the obvious solution, which was to beam it back down to Earth via laser. And so Lincoln Laboratory and the BHEX project worked together to produce a 100 gigabit per second laser optical downlink that can beam our data continuously throughout a night of observation back to stations on the Earth that will collect the data, and then we can carry them with our caveman hands to the supercomputer. So that's the premise of BHEX for this data. That's how we solve this data problem. Is we'll have small onboard storage, and then we'll be continuously beaming it back down to Earth with a face-melting laser. And it will, actually, I've been advised to not make that joke. It will not be face-melting. But it will be a very strong laser that can communicate all this data back down to Earth. So, in the last couple of minutes, I want to talk to you about just one slide on what I do specifically, which I help out with a lot of the project. I've been involved with it pretty much since its conception. But my primary focus is on measuring spin from the black hole images using this photon ring. And that's actually what this Japan conference was very highly focused on, not just updates on the spacecraft, but also updates on methods that we're actively developing to do this thing that no one's ever done before, which is measure this incredibly fine variation in this black hole shadow shape to capture how fast the black hole is spinning, which I just think is the coolest thing. So the idea is basically this. As you change the spin of the black hole, it looks a little different. And a natural question is can we learn how to use those differences to measure the black hole spin? And so what I do is I develop, as well as working on the theory of this, so it's really important to have a strong theoretical foundation for why the image looks like this when we change the spin and inclination of the black hole. We also want to be able to extract this information from the image. And so what I work on are these algorithms that can measure the black hole's photon ring from our images and extract, you find patterns to extract and measure these important black hole properties. And so we've got a lot of useful tools and published papers on this exact topic. And it's going to be, I think, one of the most exciting aspects of the project is being able to look up in the night sky with our telescope, flinging itself around the Earth, and be able to measure the spin of the black holes that we point at. And it's something I'm just incredibly excited by. So I want to close off with, the big picture. I've only had time here to give you a brief overview of some of the mission parameters and science drivers, but I want to do something that I love to do, which is just kind of take a moment to reflect on what we're trying to do here and how crazy and exciting it is. So we're going to put a spacecraft in orbit, tens of thousands of kilometers above the surface of the Earth, and connect it via laser to a network of already some of the most powerful telescopes on Earth to create a virtual telescope 3 times larger than the Earth itself. And it's going to see this photon ring of a black hole for the very first time. And this is exciting because the event horizon of a black hole, it isn't just an edge of the observable universe, but it's also a horizon beyond which is new physics, answers to our biggest fundamental questions about the universe. So yes, it's a horizon in the sense that there's stuff inside that can't get back out, and if you're outside, you do not want to go back in. But it's also a boundary between the inside of the observable universe and the outside of it, because whatever's in there we'll never ever get to see or interact with. And lastly, it's the edge of what we know and what we don't. And that's what I want you to think about when you see these images for the first time. That's what we're probing. So thank you so much for helping us listen and talk about this and helping us solve the greatest mystery in physics at the edge of the universe. And thank you to SBAU for having me here.
Questions? Raise your hand. You take it.
Yeah, sure. We've got a question here.
I had a few questions. One of my questions was, you mentioned it makes a lot of data that you don't really have much to do with. I was wondering if you guys have ever considered trying to sell that data or give that data to companies to train AI, because AI requires lots of data. And if you train the AI on lots of data about the space, the AI would make it really good at things in space and be able to help you.
So actually, I just published a paper on training a variety of machine learning and deep learning models to do exactly that, taking these data sets and training them to extract the spin inclinations of black holes. But we make a lot of data, but it's not that we don't use all of it. We do use all of it. It's just there's a disconnect between the petabytes and petabytes of data that we have and like the 128 kilobyte image that we get out at the end. And that disconnect can feel large, but all that data is helping us gather all this, get this great signal and noise and make these incredibly fine measurements. To give you some perspective on why we need to collect so much data and make all these measurements, if you took all the energy that we collect in a black hole observation, it's about the equivalent of a soap bubble popping. And that's the energy that we're getting from the black hole itself. And so you need lots of data to piece out that very faint signal. And we do that. Yeah, Magic?
Great talk, Joseph.
Thanks, man.
As always.
That's my buddy.
I was wondering if you could talk a little bit more about what signatures of the photon ring you're expecting to disprove one of those two theories, whether it's quantum mechanics or general relativity.
That's like my favorite topic. So I realize it sounds like I set him up for that, but I didn't actually. So I didn't talk too much about how we expect to use test theories of gravity. And to be honest, that's because it's a brand new area. Like, this is never in the history of humanity that we think that we have this level of resolution into these objects. But the gist of it is that shadow shape, the patch of black in the middle of all that swirling stuff, the perfect ring of light that you get when you average those images away, that shape changes, not just with the spin and inclination of the black hole, but with the physics you assume about it. So if you assume a particular theory of quantum gravity, it might change the shape a little bit. And we don't have a good handle on how it will do that. And so a big part of my work is trying to probe that, trying to say, okay, what contributions to the shape are from the properties of the black hole, and then how does that change if we test theories of quantum gravity? So, yeah.
Thanks, Joe.
Thanks. And then Richard?
Are we presently using laser transfer of data from space?
That's a good question. Not at 100 gigabits per second, I think, because it was that 100 gigabits per second laser downlink test was a brand new technology. But I believe that laser optical downlink is being used for other NASA missions, but just ones with a lot lower data rates. They can use lower power lasers. Yeah, in the back.
Yeah, so also excellent talk, by the way, Joe.
Thanks.
So another question, so you're putting the telescope 3 times the diameter of the Earth outside. Why that distance? Why not farther away? If the farther away it is, the better the image. Why not just keep moving it 10 times farther away or something?
That is a really good question. That's a lot of what we're fighting, not fighting, but like what we're struggling to balance in the proposal. So you're correct. As you get farther away, you get better and better resolution. But, oh, I wish I had a blackboard. As you get farther away, the signal of the black hole on that baseline drops dramatically. And so if you get too far away, you might not be able to even piece out the emission from the black hole on that long baseline. And so you get high resolution if you could see the emission, the signal from the black hole, but you may not be even able to see it. Also, as you get farther away, it becomes harder to beam that huge amount of data back down to Earth. And back.
Hi, Joseph. Oh, great. So with regards to the algorithm that you'd be producing to locate the photon ring, what exactly is the physical basis? Like, is it taking the data you're being fed from the black hole and running more MHD simulations from those initial conditions, or is it piecing out the brightest pixels? How exactly do your algorithms find what's the motivation?
So that's a really good question. So we have many different approaches to doing this, and they kind of fall into 2 categories. One is we assume physics and make a bunch of simulations, and then use various methods, either machine learning or some form of pattern matching, to figure out which simulation best matches reality. It's a very effective approach. It's not, you're not testing anything that way because you're assuming the physics works, but that's kind of what you were describing. The other approach is you do straight extraction from the image, and you don't assume the physics. You just extract what you think is like a peak of the emission, and you try to match it against different theories of gravity, saying, okay, I'm not going to try to measure anything. I'm going to see, say, GR predicts this shape within 10%. Do we see that? So there's a variety of approaches.
It's like a very accurate on-spots and traffic.
Exactly, yeah, for measurement. What's in the front? Yeah?
A couple questions. In electrostatics, if you have a sphere that's charged, there's no charge inside, no electric field.
Mm-hmm.
Is there gravity inside a black hole?
Yes, there definitely is. So actually, as you get further inside a black hole, the curvature of the universe increases, and the gravity gets stronger and stronger as you approach the singularity.
Well, that's as on the outside. I'm talking about on the inside.
Yeah, even on the inside.
Really?
In fact, from the perspective of the black hole, there's no outside and inside. It doesn't care about that.
Okay, the mass of the data is taken away. Where is the Fourier transform done? Is that done at where it's being collected, or is that what's transmitted down?
So when you make a measurement using an interferometer, it measures the Fourier transform. Our job is to invert that into an image. So we take the data and invert that. Yeah. Over there.
I actually have a few questions. A few of them are really short. This is probably the simple thing one that I should have to ask you. But if we're going from 4 pixels, what exactly are we going to?
So that depends on the distance of the black hole to us. But for M87, our pixel size is going from about 20 microarcseconds to about 6. So we're getting 3 times better one way, and then 3 times better the other way. So it's like a 9 times increase in resolution. That actually makes sense because the Event Horizon Telescope was about the size of the Earth, and then we're going to 3 times the size of the Earth. So it kind of tracks.
Another question was, what actually is the discrepancy between general relativity and quantum mechanics that this whole discussion was brought about on?
So there are many discrepancies, but easy two of them off the top of my head. GR tells you that you can compress stuff into basically an infinitely small point, and quantum mechanics, Heisenberg uncertainty principle says you can't, and that's like a huge violation right there. Another one is the cosmological constant. GR, we can measure the expansion of the universe and attribute that to this lambda parameter, the cosmological constant, and that's a measurement we can make. But when you ask quantum mechanics, you assume that the cosmological constant is caused by vacuum energy, and you say, okay, well, what should it be? Quantum mechanics gives you an answer that's 150 orders of magnitude wrong, and that's a huge tension right there. That could be resolved with a better theory of gravity. In the back.
Excuse me. Doesn't the data from the satellite really have to be linked to all the observations on the Earth?
Yes.
And if so, why are you using only one satellite instead of many satellites?
So that's a great question. We do have to link them together. On board, at the satellite and every station on Earth is a very precise hydrogen laser atomic clock, or I think it's they're using on a satellite, but on the Earth it's these atomic clocks that can measure nanosecond precision. When we get the data back, we have a supercomputer that solves the puzzle of lining up all these things together, accounting for the rotation of the Earth and all these amazing stuff. And then for the second question, why don't we have many? Money. When we initially conceived BHEX, it was, I think, 4 orbiters that would give us amazing resolution. But we're going to start with 1 and see how that goes.
With one satellite, now that seems like you're putting all your coins in the basket. Either it's going to work or not work.
That's true. But you could also argue that with one satellite, you can really hyper-focus to make sure it does well, instead of having 4 that you have to distribute your funding across. I think I saw one in the front, yeah.
No, I'm just having a bit of trouble visualizing how this works with
Okay,
a
so
satellite that is 3 times the diameter of the Earth away from the Earth. Earth is spinning. You have a laser that's transmitting your data each evening. But the Earth is spinning, unless this thing is explained to me, unless it is really flying around at 3 times the diameter of the Earth, that much faster in order to maintain its target for the laser. How does that work?
So that's a. I'm trying to go back to this slide. There we go. Basically, that at that diameter, and given the configuration of the spacecraft that we have set up, and given the fact that we have multiple ground stations, we're always in the view of one of our ground stations. And the technology has gotten good enough that we can like aim and get the data back down. That's an engineering problem that it turns out is achievable.
And what is the time delay then? I mean, because then you need to pre-program the shift in where that laser is going so that it reaches its destination and the data aren't lost. What is the time delay to change anything in that program given the distance away?
Oh, so we usually don't have to change stuff live. Usually stuff works. And actually the biggest problem with the EH2 is rarely hardware failures or things we have to change, but rather weather, which we won't have to deal with the spacecraft. As for the time delay, it would be based on the speed of light. So it would be 20,000 kilometers divided by the speed of light, which I'm not sure off the top of my head what that is. It wouldn't cause, that wouldn't, I think, cause too much of a problem for us. Yeah.
What do you think of the research published last year that proposes that black holes grow along with the expansion of the universe through cosmological coupling?
I read that paper. It was actually,
There's
2. It was a part 2, and actually the guy that wrote it had the same last name as me. No relation though. I wrote a blog post on it. It was really interesting. I liked the paper. The data he put forward, the analysis was good. There's been criticisms of it, but not on the basis of the data itself being flawed. It seemed like the analysis was pretty decent, but the interpretations are highly speculative. So, it is perfectly fine to speculate. That's what we do in science. The biggest criticism of saying that black holes grow with the expansion of the universe is they didn't provide a mechanism for how that would be achieved. They just kind of said, oh, if you assume this happens, it kind of explains the data. This has been done before, you can technically explain the expansion of the universe by not assuming that things are moving apart, but rather that they're getting more massive, causing the light around the redshift more. And even though I don't think anybody thinks that's what's actually happening, it's a useful cosmological tool, and it helps remind us to not get too fixated in one idea when we don't have enough evidence to completely refute others. So it was a good paper for sure, a really interesting read. But I wouldn't say that's 100%. That's overturned everything, and that's how the universe works now. But it's an excellent example of science.
I think we've all seen the rendering of a black hole that looks like a head with a sombrero around it.
Oh, yeah.
I think you showed one at the beginning. And I wonder if you could comment on where that comes from.
Sorry. Is that moving? There we go. This is almost always a black hole viewed head-on. Usually high spin, and they are simulating. Everybody, you probably know which movie these kinds of things come from. Interstellar is the most popular one. They literally did a GRMHD simulation where they took some physical parameters and simulated how light would interact with a highly spinning, you know, a rapidly rotating viewed edge-on black hole. If you look at the geometry simulations that I showed here, which these are from Charles Gamby's group, oops, sorry. You can actually see kind of jeepers creepers. I'm just waiting for PowerPoint to like go through its animation. Okay. Here we go. So if you look, this kind of looks like exactly what all those artworks look like, right? You have the ring of light, and then you have the emission in front of it. And that happens to be the black holes that are edge on. So the key thing that you're seeing with like the sphere with the hat on it, like that's a result of looking at the black hole's accretion disk right at the edge. And we can see that in our simulations. They just made it very beautiful and pretty. Something really interesting, and you guys should all do this, go back to Interstellar and look at the black hole, and you can actually see the photon ring in it. It's a very clear thing. You can see the n equals 1 and n equals 2 photon rings. But we didn't know that there were photon rings at the time. We didn't know how they worked. We just thought it was a beautiful aspect of the simulation. And it's crazy that they did these simulations right, and you know, they predicted the photon ring. I mean, they didn't really predict it because they didn't know what they were looking at the time, but they showed it before we were even really thinking about that kind of stuff. So I think that's super cool. Props to those folks. That is a really good question. So no, the data does not get redundant for two reasons. One, the more data we collect, the better we can average, and that gives us higher SNR, which is really important because, like I said, the data that we get is fainter as you go farther along your baseline length, and it's already really faint, even for BHEX. The second thing is if you revisit the same point in the Fourier space multiple times, you can start learning about the time variability of the black hole. So how is it evolving with time? And then we can match that to our simulations and say, oh, the black hole probably has this properties, this fluid flow velocity, this magnetic field strength, this accretion rate. So it's redundancy, but as always in science, redundancy is always a very good thing. In the back?
So assuming that the Black Hole Explorer is a success, 10 years from now when it launches. Yes, it's a great success. You've got your new picture. It's a little less blurry than the first one, and you can see the photon ring.
I'm vision casting right now.
Yes. What would the next steps be for increasing the resolution even further? Would it be additional satellites, like someone over here mentioned, or various distances away?
So additional satellites gets us, at the same orbit distance, gets us better coverage in terms of time domain. Like we can make movies, which I published a paper on that. I think it's extremely cool, and we could do it with multiple satellites. For increasing our resolution, you want to build your spacecraft at a higher orbit, so we hope technology will get better to send the data back and make these more sensitive observations. Another possibility people have discussed is putting a radio telescope in a crater on the far side of the moon or on Mars, which is very cool. Not our proposal. But so there's lots of ways to do it, for sure. And like, while with the EHT, we can study like 2 black holes. With BHEX, we'll be able to study dozens. And so it'll be a lot more data for a lot larger sample for a lot longer time. Yeah. Matt.
Would this telescope only be useful for looking at black holes or other celestial bodies?
So we'll be primarily using it for black holes, and there's a specific reason for that. The wavelength of light that we observe at is very specifically tuned to the radiation that black holes put out in their immediate vicinity. And there's nothing else in the universe that really creates that kind of insane radio waves, insane radio emissions. So we can look at anything, presumably, that emits that kind of radio light, it's right part of the sky where our telescopes can see it and that kind of thing. But our focus will be primarily black holes and their jets.
I know I have a few questions. What orbit will the satellite? What orbit will the satellite take?
It'll be, I believe, a mid-Earth orbit, 20,000 kilometers above the Earth. That's either mid or low, I was forgetting.
And you mentioned supercomputers a few times. Which applications will they be at?
Bonn, Germany, and Haystack Observatory in Massachusetts. Though they already exist there, they're called correlators, and they align the data.
Will they be provided by?
They already exist. We've already built them, and they already function.
Your project built them, or?
The Event Horizon Telescope built them. which is our project. We're like a spin-off, like the Flash from Arrow. Or, yeah.
What is the size of these massive black holes, and what is the spin rate of these black holes?
Oh, okay, so the spin rate is a tougher question because we can't see the photon ring, so it's harder to pin that down. But for the size, we have very good constraints on the size. So it's actually really fun thinking about how big these things are and yet how small. So Saggitarius star in the center of our Milky Way is 25,000 light years away. It's pretty shrimpy as far as supermassive black holes go. It is a mere 4 million solar masses. So, and it also is, in terms of size, it's about the orbit of Mercury in size. So yeah, and that's really amazing because it has a light crossing time or a dynamical time scale, stuff whips around it, on the time scale of like 30 minutes. For those, any astronomers here know the orbital period of Mercury?
88.
88 days, right. So while Mercury takes 88 days to go around the sun, the stuff goes around Saggitarius star about the same size in like 88 minutes. So it's very, very active. M87 is a real, big black hole, and it's about 6.5 billion solar masses. And it takes about, one it takes up is about the orbit of Jupiter. That's for the central black hole. If you look at the image itself, the image, it's hard to describe how big this image is, but I will give it my best shot. Let me pull up M87. So, if you look at the image itself, if you put the sun right at the center, you wouldn't even be able to see the solar system. It would be too small. Voyager 1 would be just inside the black part. And this is far beyond anything human had time to touch. This distance, it takes like 4 days to cross from one side of the black hole to the other. So very, very, very large.
Hey, thank you.
Field work would be used.
Yeah, there's some really good figures I can show too.
So looking at the resolution that you want to get, you addressed the diameter, but you didn't address the wavelength, but you mentioned radio waves, which are very large, so it doesn't put out any short wavelengths?
Yeah, actually, so the Event Horizon Telescope operated at 230 gigahertz, which is a wavelength of about 1.3 millimeters. And one of the things we're doing with BHEX is we're going to shorter wavelengths. So we're increasing the frequency to 320 gigahertz, which right off the bat is like a 50% increase in resolution without going out to those farther distances. So we are for sure playing with frequency as well. But there's certain things that restrict that. So for example, why didn't we do 280 gigahertz, right? We pick our frequencies based on what the atmosphere doesn't absorb. We want all the light possible to get through the atmosphere. 230 gigahertz is one dip in the atmosphere where it doesn't absorb that light, and then 300 gigahertz roughly is the next, or I think it's 345. And so even though we have this telescope that's not affected by the atmosphere, the ground stations are. And so we have to work with their limitations. Yeah.
I have 3 questions. The first one, are white holes real?
They're a theoretical construct. We've never observed them.
Do you believe they're real? More yes or more no?
Science doesn't ask for your beliefs. It asks for your eyes and ears.
The second question I was wondering is, I've heard there's an idea that the entire universe is inside a black hole. Do you think that idea has any merit to it?
It's a very useful tool that's called the holographic principle. And holography is an extremely useful tool for the kinds of calculations that we're doing here. But whether or not it's real, I have no idea, and nobody does. And anybody that tells you they do is lying.
No. According to the boundless wisdom of YouTube, what I've heard about quantum mechanics and general relativity, one of the differences I've heard, at least, is that general relativity is usually for things an atom or larger, and quantum mechanics is usually designed for things subatomic and anything below that level, up and down to the Planck length and nothing below that. But if that's true, then couldn't you just use general relativity for anything larger than an atom for a black hole, and quantum mechanics for anything a size smaller? Or am I mistaken, or is it because there's no mathematical model for quantum gravity, so that idea doesn't work?
So the problem becomes when you have things that are much more massive to the point where you need general relativity, but also so small that you need quantum mechanics. And even though I showed you really big black holes, I showed you that a black hole, an Earth-sized an Earth-mass black hole, you compress into a marble. If you get much less than that, you're starting to approach quantum mechanical scales. So black holes are absolutely a regime where black holes are a regime where you can use both GR and quantum mechanics. Yeah.
Imagine that we, this group here, could authorize release of funds to completely fund this project for you. And you know, this is a pretty friendly crowd out there.
Yeah.
So
I'll pass around.
my question is, in the event that the money is spent, what's in it for us,
Oh,
other than the knowledge?
the knowledge. Well, so a couple things. Like the technology that we develop as part of all NASA missions eventually works its way back onto us. The phones in your pocket are based on technologies that were developed by NASA missions. Things as simple as like a heat preserving jacket, like the ones that are made of foil, like those are based on what NASA uses in astronaut suits. I would not, especially in this day and age, I can't put enough value on exploration for exploration's sake. I think that if you ask what virtues make human beings humans, it's the pioneering, spirit. And I think that's a lot like part of what we're doing here is we now know there's an edge to our universe. Like, let's go find it.
Joseph Farah, you did good. We're gonna have him back someday, and all that quantum stuff really got me entangled. You don't know what that means, ask your friend next to you. We're about to close things down, but I wanted to get you, I asked the merchandise manager who always gives me an incredible cup that we sell for $10, our SBAU ceramic cup. Why are we giving him that? And she said, we gave him one.
That's true. I already have one.
Okay, that's your morning breakfast, and this is your new tote bag. Thanks so much. Jerry, did you have any questions before we go? One from the president? Did you give me the mic here?
Well, I did wonder, you showed two sort of graphics for putting GR and quantum together.
That was
quantum gravity.
Oh yeah, and string theory.
And string theory. But what do you think of Jim Hartle's boundless proposition?
Okay.
And he and Stephen Hawking were working on that with each master.
I'm unfortunately not smart enough to be able to answer that question. Yeah. We did the same as I'm actually the Jim and Mary Jo Hartle fellows at UCSB. But this is the kind of stuff that I want to learn. Like those guys are much smarter than I am. So.
Lines for that are that it does away with the singularities. There aren't singularities at the beginning of the Big Bang or the center of a black hole, but you have to accept the concept of imaginary time. And that stretches everybody's imagination.
I would have to read more about that. Yeah, I don't think I could make an assessment. That sounds really interesting.
Excellent. I just realized we pay for this service, so we're not very involved. San Bernardino. Tell your friends and take our word to the assembly, Greg Hart. They'll streamline
To do that, you have to offset spending. And so, to do that,